All right. So this very first section that we talk about in this course, let me back that up. The first chapter that we're going to be covering is chapter 2, and chapter 2 deals with a really important area in math called set theory. We don't go deep into it because set theory is actually like an upper division course you would take as a math major. But there's some accessible stuff within set theory that we can talk about at this level. So just a quick little side note, set theory is something that mathematicians are really interested in because it kind of represents the most fundamental basic level of mathematics. In fact, it turns out that we define pretty much everything in higher math in terms of sets. We actually define numbers in terms of sets. Everything boils down to this concept of a set. So it becomes really important to understand how these things called sets work and what we can do with them. Now, the idea of a set is not really an unfamiliar one. The definition is a little vague, but what we define a set to be is a collection of objects. Notice it doesn't say a collection of numbers or a collection of mathematical objects. It's just objects, you know. And it's vague for a reason, because we want the definition of a set to be kind of general. We want it to encompass a lot of different possible things so that we can use it for all of those things. So that's a set, a collection of objects, and we'll get into more detail in a moment. The objects that belong to a set are called elements. So that's the term that you're going to hear me use a lot throughout this first chapter that we cover. Now, for our purposes, we're going to be describing sets in three main ways. The first one is with sort of an English description, or we call it a word description. So examples would be if I were to say the set of all positive integers. If you don't know what an integer is, we're going to define that a little bit later in this section. That's one example of a set. The set of all days of the week starting with the letter S. So that's a set of objects that would not be numbers. You know, this first set includes numbers. This involves something that doesn't seem mathematical at all, and that's because it doesn't need to be to fit this description. The set of all letters of the alphabet that are not vowels. Another way of describing that set would be the set of all letters of the alphabet that are consonants. That's a letter that's not a vowel. I described it this way, though, because oftentimes we want to define sets in terms of what they don't include. There's reasons to want to be able to do that, which we'll see later on. And then finally, my attempt at humor, the set of all frogs named Biff. Kind of a dumb example, but again, sets can be filled with dumb things. It doesn't really matter. Sets can be, they can contain any kind of object. So these are the kind of the most basic level of describing what a set is, and it's also going to be the least useful for most purposes. We want something a little bit more concrete, a little bit more tangible most of the time. So another way of describing what a set is, or what a set looks like, is by using something called listing notation, or it's also called roster notation. And this is an actual listing, as the name implies, of all of the elements belonging to a set. So some examples here. This set contains the elements 2, 3, 5, and 7. It's a set with only 4 elements inside of it, and they're all shown here. This set contains the numbers 1, 2, 3, 4, and then we get this ellipsis here, this dot, dot, dot. The ellipsis implies a pattern that continues indefinitely. So this set actually contains an infinite number of elements. I obviously can't write an infinite number of numbers. You know, there's not enough time or paper to do that. So instead, we just indicate that using the ellipsis. You'll see that a lot. Here's a set that contains that doesn't contain any numbers at all. This set contains the words red, blue, and yellow. So it contains the primary colors. And then one more example, this set contains the Greek letters alpha, beta, gamma, and then you see the dot, dot, dot here again, but rather than leave it at the dot, 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 we end it at the Greek letter omega, which is the last letter of the Greek alphabet. And you don't need to know the Greek alphabet, but this is basically the first 3 letters of the Greek alphabet, ... and then the last. So what this indicates is that this set contains all of the letters of the Greek alphabet, but because there's so many of them, we don't really want to take the time to list them all out. The ... here helps us shorten that notation, so we don't have to write everything. It's clear enough that this is the set of all Greek letters. Okay, so just a few examples in listing notation. Set builder notation is simultaneously the most useful notation for mathematical purposes, and also the most frustrating one for students who are new to the concept, because it can be difficult to understand. So set builder notation is the reason it's so useful is because there's a lot of times where it's not practical to be able to list the numbers using some kind of a pattern like this. You know, an example would be the set of all numbers between 0 and 1. Well, there's an infinite number of numbers between 0 and 1. You have 0.1, 0.11, 0.111, 0, you know, and you can see how I can go on forever. But in between all of those numbers are other real numbers, you know, 0. You know, like 101 and so on and so forth. So you can't really list them out in any kind of order. You can't. It's not clear if I use an ellipsis what that would mean. This notation is not sufficient for describing sets like that. Set builder notation is equipped to do that. So the way set builder notation works, just like in listing notation, we use these curly brackets. Those curly brackets indicate that you're talking about a set. But then the vertical bar that we see here is what's indicating that we're looking at set builder notation. So in set builder notation, there's 2 sides to this bar. The side on the left tells me what the elements of this set roughly look like, you know, and the expression on the right of that vertical bar is a property that all elements of this set have to satisfy in order to belong there. And here's how we read this. When you see this vertical bar, you read that as such that. You say the words such that when you see this. So this first set here, I describe this as the set of all x such that x is greater than or equal to 0. This is the set of all non-negative real numbers. That's another way of describing this. That property defines the elements that belong here. Here's another example. In this case, instead of saying the set of all x, I say the set of all ordered pairs, x, y. This is an ordered pair. So the elements of this set don't look like single numbers anymore. They look like ordered pairs of numbers. This is the set of all ordered pairs of real numbers x and y such that x squared plus y squared equals 1. If you remember from intermediate algebra, this is the equation for the unit circle. That's the circle of radius 1 centered at the origin. And the set of all ordered pairs satisfying this would be exactly the set of all points on the unit circle. Not important for you to know that off the top of your head, because that's not our aim here. We're not talking about conic sections and stuff like that. It's really just to understand this notation. So the things in this set look like ordered pairs, and they have to be ordered pairs that satisfy this property. This last set here, which we'll talk about again in a little bit, it says this is the set of all numbers of the form p over q. So these numbers in here look like fractions or quotients, such that p and q are integers and q is not equal to 0. So again, that term integer, if you don't remember what that means, we're going to talk about that in a little bit. This condition here, q does not equal 0, is necessary because if q could equal 0, then this fraction would be dividing by 0, and we know that we can't do that. So this is preventing that divide by 0 error that you're not allowed to make. Okay, so with that said, let's move on here. One important characteristic of sets that's not mentioned in the definition, but it's always there, is that you're not allowed to repeat elements when you're writing a set out. So for example, this does not work to write something like this, the set containing the elements 1, 1, 1, and 2. we can't have 1 showing up more than once. Okay, sets do not contain multiple copies of the same element. So that's not going to work. Now, when we're talking about sets in slightly more abstract terms, oftentimes we want to label a set with something. So oftentimes we're going to use capital letters to notate a set if we're talking about a set. And if we want to talk about some general element of a set, we tend to use lowercase letters. This little symbol right here, which is a variation on the Greek letter epsilon, is the symbol that tells us if a particular element belongs to a particular set. And we read this as is an element of. So when you see this symbol right here, this says X is an element of A. X represents an element, A represents a set that contains this X here, among other elements. If we put a little line or a slash through that symbol, we read that as is not an element of. So if I say X is not an element of A, it means exactly what it says. X is an object that doesn't belong to A, or doesn't live in A. So let's look at some examples. These examples are pretty straightforward. They're just true or false. So starting with this one, we want to determine if this statement is true or false. And both of these you can think of as statements. This is stating that X is an element of A, and this is stating that X is not an element of A. Statements are always either true or false. Is -1 an element of this set here? Well, I can see that -1 is one of the elements listed in this set. So this would be true. -1 is an element of that set. True. Okay. This next example says 1/2 is not an element of this set here. This set contains the fractions 1/4, 1/3, and 1/2. 1/2 does belong to this set, so it would be incorrect to say that it does not belong to this set. In this case, I would say false. Okay. Now this example here uses set builder notation. Remember, this is a little bit trickier in general because you don't get to see listed out all of those elements. You just have to use the property that defines the element of the elements of that set to make this determination. Is it true to say that -pi is an element of the set of all x such that x is greater than 0? Well, again, remember, the elements in this set look like numbers, single numbers, not ordered pairs or anything like that. And the property they have to satisfy is that they have to be greater than 0. Another way of describing this exact same set is the set of all positive real numbers. If a number is greater than 0, that makes it positive. Now pi is positive, but putting the minus in front of it makes it negative. That's a -pi. So this should not belong to this set if this set only contains positive numbers because this number is negative. I would say false in this case as well. Okay? All right. So as I said before, we would talk about the integers. We're actually going to talk about a few different important sets of numbers. There's a few sets of numbers that show up so frequently in math that they get their own name. And we're going to go over those briefly here. So the first one is the set of what we call the natural numbers. These are sometimes called the counting numbers. It's literally the numbers 1, 2, 3, 4, and so on. This is an infinite set. The ellipsis here indicates that. In fact, all of these are infinite sets. They have infinitely many elements in them. That's the symbol that we use for that is what we call a blackboard bold capital N. You don't need to know the term blackboard bold, but it's just sort of the description. It looks like an N with kind of a thick middle section there. The set of whole numbers is almost the exact same thing as the natural numbers. The only difference is that it includes the number 0. So it's 0, 1, 2, 3, and so on. That number 0 is one of the most important numbers in math, which is why including it in this set is significant enough to think of it as a different set and give it a new name. The symbol we use for the whole numbers is just a regular capital W. Now the integers we think of as the set of whole numbers with all of the negative whole numbers included. So 0, 1, 2, 3, and so on, but also -1, -2, -3, and so on. So I have an ellipsis in both directions this way, going including all the negatives this way, all the positives this way. But the key thing here is that integers are not fractions. They are positive or negative whole numbers. Okay. Moving past that, rational numbers. What are the rational numbers? Well, we saw this description for a set earlier. The rational numbers are the set of all fractions p over q such that p and q are integers and q is not equal to 0. The symbol that we use for the rational numbers is a blackboard bold capital Q, which has this kind of thick outer edge here. Q stands for quotient, and that's what a fraction is. It's a quotient. That's why we use that. I didn't mention the symbol for integers. We use a Z for that, blackboard bold Z. It might seem a little weird that we use a Z instead of an I, and the reason for that is because not all math is done by English speakers. The Z comes from the German word for number. I believe it's Zahlen, something like that. So that's where that symbol comes from. Real numbers. What is a real number? Well, a real number is any number that can be expressed as a decimal. And here's that description given to us in set builder notation. Real numbers, we use a blackboard bold capital R as its symbol. Okay? And then finally, the irrational numbers, which we don't assign a symbol to, but we do talk about them fairly often. The irrational numbers are any real number. It's the set of all real numbers, I should say, that are not rational. Now, important thing to point out here, when I say up here that the rational numbers is the set of all fractions, we need to be careful with that definition because there are numbers that don't look like fractions but are still rational numbers. An example is this, 0.1. This is a rational number, but it doesn't look like a fraction. And why is that? Well, it's because I can write it as a fraction. And that's key. So when we talk about rational numbers, really it's the set of all numbers that can be represented as a fraction, even if they don't initially look that way. In pre-algebra, you learn that any number that has a terminating decimal representation, so meaning it doesn't go on forever, or any number that has a non-terminating decimal representation, meaning it goes on forever, but has some kind of repeating pattern, those are all rational numbers. Irrational numbers, as a decimal, will look like a number that has a non-terminating decimal representation, meaning the digits go on forever, and in addition to that, there's no repeating pattern to it. Pi is an example of an irrational number. So there's no overlap between these sets. If a number is rational, then it can't be irrational, and vice versa. And if you were to take the rational numbers and the irrational numbers and put them together into one big set, that's something that we call a union, and we're going to talk about that in a different section. Then you get the real numbers. So the real numbers is the set of all rational and irrational numbers, and that's another way of defining that set. Okay, so those sets are really important. We use them a lot. It's important to know those names and those symbols. Moving on. Another important concept when we talk about sets is this concept of cardinality, or what we call a cardinal number. And a cardinal number for a set is literally just the number of elements that belong to that set. It's telling us essentially what the size of a set is based on the number of elements it contains. We use this symbol for it, and I read this as n of a, or the cardinal number of a. Now, there's one important set that initially seems a little bizarre that we'd even want to talk about it, and ends up being extremely useful for the purposes of set theory, something that we call the empty set. And it's the set that contains nothing. It has no elements inside of it, hence the name empty set. We sometimes also call it the null set. And we commonly use this symbol for it, this circle with a slash through it. Occasionally you see this used for the empty set as well. It's not as common, but it's the curly brackets that we use to describe sets, and there's just nothing between the curly brackets. It's empty, right? So let's look at some examples where we want to determine cardinality. What is the cardinality of this set here? 1, 3, 5, 7, 9. Well, this is an easy one. The cardinality, which I would write n of g, is 5, because there's 5 numbers in this set. Really straightforward. If only all these problems could be that easy, though. This next set, A, is not described in term, or it's not explicitly showing me all of the elements of that set. How do I show, or how do I determine the cardinal number of this set if I don't get to see everything that lives in it? Well, that's not too difficult to do, because there is a pattern apparent here. 5, 10, 15. I imagine the next number would have been 20. The dot, dot, dot here indicates a pattern. Remember that. And then it ends at 100. So this is the set of all multiples of 5 between 5 and 100, including 5 and 100. The easiest way to determine this, instead of just listing them all out and counting them one by one, is to use division. 100 is the ending point, and if I divide that by 5, I would get the total number of multiples of 5, from 5 to 100. 100 divided by 5 is 20. So the cardinal number for this set A would actually have to be 20. Okay, how about this next one? H is equal to the set of all x such that x is an integer and x is greater than -3 but less than or equal to 2. Okay, well, this is given to me in set builder notation, but this is an example where listing notation would be more helpful for the purpose of finding cardinality. And so what I'm going to do is rewrite this set, but list out the elements. Now, x is an integer here, so that means I'm not considering fractions. I'm only thinking of positive or negative whole numbers, including 0. And x cannot be -3. It has to be greater than -3. So the next integer that's greater than -3 would be -2. And then -1 would also be greater than -3, but still less than or equal to 2. In fact, I'm just going to write out all the numbers between -3 and +2. 0, 1. And I get to use 2 because it says x is less than or equal to 2, meaning 2 is a valid number to use for x here. So once again, if I counted these, I see 5 elements in this set. I would say that n of h is equal to 5. 5 elements in the set. What's the cardinality of the empty set? This is our last example here. Well, if a set contains nothing, then that's another way of saying that it has 0 elements. So the cardinality of the empty set is 0. It's the only set that has a cardinality of 0. All right. So we're almost done here. One last thing to talk about concerning sets, and that's something that we call set equality. What does it mean if we say that two sets are equal? So suppose we have these two sets, A and B. We say that they're equal, and we use the usual equal symbol in between them to indicate that. If we can say the following: if every element of A belongs to B, and if every element of B belongs to A. So everything in A is going to be in B, and everything in B is going to be in A. In other words, both sets have exactly the same elements, and neither set has anything that the other set doesn't. Okay, that is what we call, or that's how we say indicate that two sets are equal to each other. This in symbols is saying the same thing we just described it there. A is equal to B if the following conditions both simultaneously hold. If X is in A, then X is in B. If X is an element of B, then X is an element of A. Okay? If two sets are not equal to each other, we can use the not equal to symbol to indicate that. So to wrap up this section, we're going to look at some examples of determining whether two sets are equal to each other. So in this first one, A is equal to the set containing the elements 1, 3, and 5. B is the set of all x such that x is an odd number. So if I'm looking at these conditions, if x is in A, then x is in B. That's true for this first example here, because if x is in A, then the only numbers that are in A are the numbers 1, 3, and 5. All three of those are odd numbers. B is the set of all odd numbers. All of these would belong to B. Where we run into trouble is this second condition here. If x belongs to B, then x belongs to A. Well, there's more odd numbers out there than just these three. For example, B would contain the number 7. In fact, it would contain the number -1. because negative numbers can be odd as well. Those numbers are not in A. So that prevents this from being an example of set equality. I would say A is not equal to B for this first case. Okay. Let's look at this next one. J is the set of all x such that x is equal to 0 or x is a natural number. That's our first set. The second set is just showing a W. But remember, W represents the set of whole numbers that was up here in our chart that we looked at earlier, or our table. So in this case, I would say that these two sets are in fact equal to each other. If x belongs to this first set here, then it's one of these two things. It's either the number 0, which we know belongs to the whole numbers, or it's a natural number, and the whole numbers include all of the natural numbers as well. And you can do the same thing in reverse. If x is a whole number, then it's either 0 or a natural number. Here I would say that J is equal to W. Okay, they're the same set, just described in different ways. Let's look at this next one here, C. R is the set of all natural numbers between 5 and 8, and Q is equal to the set containing the elements 5, 6, 7, and 8. Looking at this initially, you might be tempted to say that R and Q are equal, but they're actually not. R is not equal to Q. And the reason for that is because of how we interpret the word between. When you see the word between show up, which you will in some of the homework problems for this section, we mean literally between, as in not including 5 and 8. The only natural numbers that are between 5 and 8 are the numbers 6 and 7. 5 is not considered to be between itself and 8. Okay, so if these two sets were to be equal to each other, then Q would have had to only have the numbers 6 and 7. It has too many elements to be equal to this set R here. One last example, this set S. S is the set of all ordered pairs of real numbers, x, y, such that x is a natural number less than 3, and y is equal to 2x. Now this might be the most complicated looking set that we've encountered, but in fact it's a very small set if we were to try and explicitly write it out. So let's look at it, before we look at T, let's look at another way of describing S. See if I can do it in roster notation or listing notation. So remember, we're looking at ordered pairs. There's a first element, first component and a second component here. We're calling them x and y. X is a natural number less than 3. There's only two natural numbers that are less than 3. There's the number 1, and then there's the number 2. So those are the only two possible values that I can use for this first coordinate here. What about the second coordinate, y? Well, y is related to x according to this definition here. Y is equal to 2x. So in this case, if x is equal to 1, then y is equal to 2 times 1, which is 2. If x is equal to 2, like it is here, then y should equal double that, 2 times 2, which is 4. And if you notice, by writing set S in listing notation, instead of just trying to visualize it based on set builder notation, I can see that S and T are actually the same exact set. So S is equal to T. Okay, that's going to wrap up our first section of Chapter 2.